In this video, we'll discuss the basics and some guidelines when it comes to designing with multi-layer ceramic capacitors, or MLCCs for short. Multi-layer ceramic capacitors, especially these SMD types, you'll find in pretty much any modern hardware design. Going to a typical distributor's website, we can see there's different manufacturers, parameters such as capacitance, voltage rating, various dielectric types, tolerances, case codes, and so on, which can be very overwhelming if you're just starting out, but you do have to pay attention to all of these parameters depending on the situation and depending on the application. And I'd like to give you some guidelines and some ideas in this video. We'll also be looking at typical manufacturers' websites, seeing what tools we can use to make our design choices easier and to guide us to choosing specific parts, such as looking at DC bias characteristics, temperature characteristics, and various other non-idealities of these real-world capacitors. I'll also show you some simple SPICE simulations of non-ideal capacitors so we can analyze their frequency responses, which will be important in future videos when we're designing filters and so on. Thank you very much to Altium for sponsoring this video. If you'd like to give Altium Designer a try for yourself, make sure to check out the link in the description below, or go to altium.com/yt/philslab, and you can get yourself an Altium Designer free trial, check out the cool new Altium 365 features, as well as to get 25% off your first license purchase. To help you get started with your free Altium Designer trial, make sure to check out video number 41 on my channel, which gives you a complete Altium Designer walkthrough of an STM32 PCB design, all the way from project creation through to getting your design manufactured and assembled. I won't be covering all of the basics in this video. There are many resources online and in books which tell you all about this, and I'll leave some links in the description below. I'd like to talk about MLCCs, that means multi-layer ceramic capacitors, specifically with regard to real-world applications, non-idealities, and stuff that isn't discussed very much in most online resources. Multi-layer ceramic capacitors, MLCCs, you will find on pretty much any PCB, if that's for power decoupling, if it's for filtering, if it's for bypassing, or for example timing circuitry. They'll be used anywhere. We'll only be talking about SMD capacitors in this video, and these come in various standard sizes. You'll have seen imperial and metric, which can be quite confusing because imperial sizes such as 0201 also exist in metric as 0201. When I talk about passives and these component sizes, I typically will always be talking about imperial. So on the right-hand side here, we can see from very small components such as 0201s, which you might need for BGA power delivery, up to 1210 capacitors right at the bottom, which are very large, and therefore, as we'll see later, will also have potential for much larger capacitances and higher voltage ratings. If you're new to this, you probably will have just chosen your capacitors based on their nominal capacitance, so you might have chosen a 1 microfarad capacitor with some sort of tolerance, plus minus 10%, plus minus 20%. You might also have considered the voltage rating, such as 16 volts, 10 volts, 25 volts, and so on, but many people might not have considered the actual dielectric and disregarded that completely. But I'd like to talk more about this in this video. For MLCCs, there's a standard that defines 4 classes of multi-layer ceramic capacitors. In this video, we'll be predominantly only talking about class 2 ceramic capacitors, as they are, in my eyes, the most common, but the most common classes are 1 and 2. Class 1 capacitors, typically NPO or COG, offer the highest capacitance stability and accuracy, so they might be plus minus 5% parts. Their capacitance won't vary with applied DC voltage or much with temperature and so on. However, MLCC Class 2 capacitors will enable much higher capacitances for the same package size. So you might get 1210 capacitors with 100 microfarads capacitance, which is very large considering it's still a very small package size. However, at the expense of this higher capacitance per given package size, so their volumetric efficiency, they'll have a lower stability and accuracy, meaning, as we'll see later as well, that applying a DC voltage across one of these Class 2 MLCC capacitors decreases their capacitances and alters their properties. All this being said, and all these parameters we do need to take into account, and these need to be chosen carefully depending on the situation. For example, choosing a power decoupling capacitor for a high-speed digital IC in a hot environment will be different to choosing an AC coupling capacitor in an audio path, which again will be different to choosing a crystal load capacitor. I'll give you some guidelines at the end of this video, and you'll see how to choose various parameters as we go along in this video. But keep in mind, you can't just simply pick a 100 nanofarad part and be done with it. It really depends on the situation. We'll be looking predominantly at Class 2 multi-layer ceramic capacitors. We'll be doing this as these are pretty much the most common type of MLCCs, in particular in modern digital designs you will see. They're cost-effective with large possible capacitances in fairly small packages. They're useful for decoupling, bypassing, certain types of filtering, and so on. What you will have probably seen for Class 2 multi-layer ceramic capacitors, and we'll look at a distributor part search in just a second, is this 3-digit code for Class 2 multi-layer ceramic capacitors, for example. This 3-digit code, for example X5R, X7R, Y5V, and so on, defines the maximum expected capacitance change over a given operating temperature range. So on the top right-hand table, the first character, for example X, Y, or Z, defines the lowest operating temperature. So X gives us minus 55 degrees, Y minus 30, and so on. The second character, or digit, gives us the maximum upper temperature range. So an X5R capacitor will range from minus 55 degrees up to plus 85 degrees in operating temperature. The last character will tell us about the maximum capacitance change over the temperature range. So an X5R, again, minus 55 to plus 85 degrees, and R gives us a maximum plus minus 15% capacitance change over that temperature range. So fairly easy to figure out, depending on what temperature you expect your environment to be in, of course always add a safety margin, and then also an allowed tolerance margin depending on temperature. However, as we'll see, this is not the only thing we'll need to be taking into account. Going back to the distributor part search, going to the dielectric column, we can really see then some familiar terms now. So we find X5R, X5S, X7R, X7S, and so on. And these will be Class 2 ceramic capacitors, which have the properties we just described. As a guideline, and we'll see this later on as well, Class 2 ceramic capacitors aren't always that great and only should be used in certain situations, although they are very common. For example, in the application you shouldn't probably be using them in is in audio applications in the audio signal path, as Class 2 multilayer ceramic capacitors exhibit piezoelectric effects which can lead to microphonics which are very much audible. Additional problems when it comes to Class 2 multilayer ceramic capacitors is that they have a capacitance change, and oftentimes a very large capacitance change, for example due to applied DC bias, applied AC signal and frequency, what temperature we're at, and also aging. And all of these parameters and all of these influences in capacitance change of course need to be taken into account when you're designing your system. Imagine you're designing an RC filter with a certain cutoff frequency, but depending on the DC bias, depending on the temperature, depending on the age, your cutoff frequency will change. And in critical systems, this of course can be rather detrimental. Let's check out a real Class 2 ceramic capacitor and see these deratings in effect. I quite like Murata as a manufacturer. I'll just go within stock, and let's just go for a 1 microfarad, 10 volt X7R capacitor. So a fairly large temperature range. And I'd like an 0805, that's an imperial case code. I'll just click apply filters. I'll sort by price, and let's just choose the cheapest. So this one here. We can really get a feel for the pricing. You can see a 1 microfarad capacitor, low quantities 15 cents, large quantities about 2 cents apart. Again, these are all nominal values. So nominal 1 microfarads, voltage rating is 10 volts, we have dielectric and a tolerance, and of course a case size. Now let's copy this manufacturer part number and go to the manufacturer website and their tool. Murata's tool happens to be called Sim Surfing. Then in the part number search on the left hand side, I can enter the part we just found on Mouser, and here's our part. We'll ignore the fact that it's not recommended for new designs. Of course, you shouldn't be using this in a new design if it's NRND, but we're more interested in the bias characteristics and so on. On the top hand side, we can see under basics, we can see a C DC bias. If we click on that, we want to see the capacitance change, or the nominal capacitance with an applied DC bias. So I click on this opens up a graph. As we can see, at 0 volts applied DC bias, we have about 1 microfarad of capacitance, but as we increase the DC bias up to about 10 volts, we can see this capacitance has already dropped by about 20%. Now this particular capacitor actually isn't that bad, but if we open a different capacitor, let me just choose a random capacitor here and then do DC bias again, we can see over, for example, this other capacitor's maximum allowed voltage range, so this is a 0 to 4 volt capacitor. At 0 volts, it's 300 microfarads, but at 4 volts, which is the maximum allowed DC bias, it's already dropped to a third of the original capacitance. This is, of course, rather significant, and this needs to be taken into account. Another thing is, of course, the capacitance depending on the temperature, so we can open up this graph as well, and we can see we have quite strong fluctuations depending on what operating temperature we have. There are many other different graphs we can open up here, and I'd strongly suggest playing around with this tool, looking at different capacitors, looking at different case sizes, and seeing how the deratings differ between them. So even with applied AC voltage, we'll get a capacitance change. So this is a real problem, or can be a problem, in fairly critical applications using Class 2 multilayer ceramic capacitors. Another issue when it comes to capacitors, and this is not just for ceramic capacitors, this is of course for aluminium, tantalum, and so on, is the capacitor's frequency response. Unfortunately, a capacitor, as we saw maybe at university on some books, isn't just a capacitor, for example on the left-hand side here. The equivalent circuit of a capacitor is actually the one shown on the right-hand side. We have some sort of leakage resistance, we have a series resistance or ESR, and we have a series or parasitic inductance. This is far closer to what we actually have in the real world than this simple capacitor shown on the left-hand side. The problem with this circuit, or the non-ideal circuit, the one we have more in the real world, is that we have a limited effective frequency range for decoupling and filtering. If we plot the impedance profile of this equivalent circuit, so with a capacitance, series resistance, and series inductance, if we plot this impedance versus frequency, we see the plot on the right-hand side, and this is very typical, this V-shaped plot. Below a certain frequency, we have a decreasing impedance characteristic, what we would expect from an ideal capacitor. As we increase frequency, the impedance decreases, or the reactance of that capacitor decreases. The problem is due to this equivalent series inductance, at a certain frequency, or from a certain frequency, this equivalent series inductance will dominate. And this happens after this V point to the right at the bottom, and this is known as the self-resonant frequency. Above that self-resonant frequency, our real-world capacitor doesn't actually behave as a capacitor anymore. It behaves like an inductor. And therefore, for example, filtering or bypassing decoupling, it's pretty useless around or from that point, from this self-resonant frequency. As you can see, after the self-resonant frequency, we have an upward-sloping impedance profile, which is typical of an inductor, where the reactance increases with increase in frequency. This is another thing to keep in mind. Up to the self-resonant frequency, which is typically for multi-layer ceramic capacitors around a couple of megahertz, we can use this as a capacitor. It's fine for decoupling and filtering, but from that point and above that point, it's useless for decoupling and filtering. This impedance characteristic depends, of course, on the capacitance. It depends on these various parasitics, such as the series resistance, the inductance, and so on. Again, you can extract this information from manufacturer tools or datasheets. So going to our sim surfing tool again from Murata, at the top we can go to frequency characteristics, and I've just chosen this random capacitor and plot the magnitude of the impedance versus frequency, and we'll see this very, very similar graph here. And again, this is for a different capacitor, so it'll have different ESRs, ESLs, and so on, but we still see this typical V shape where below about 100, 200 kilohertz, it behaves as a capacitor, but above that, above the self-resonant frequency, it behaves inductively. I'd strongly suggest playing around with this because this will depend on the dielectric, it depends on the package size, what these parasitic values are. As you can see here, compared to the previous capacitor we saw in the image before, which was a 100 nanofarad 0402 package, this larger 1210 package here has a far lower self-resonant frequency, and therefore it's only useful up to about 100 or 200 kilohertz as a bypass or filtering capacitor. For simulation, it's of course very useful to find the ESR and ESL. The problem is we have to do approximations here, as ESR and ESL are also frequency-dependent parameters, as you can also get from these sim surfing or manufacturer tools. But for very basic simulation, and I'll show you how to do one in just a second, we need to find the three main parameters of our model, which is the capacitance, C, the series resistance, and the series inductance. The capacitance, we have to take into account our derating, so the DC bias, if there's an AC voltage applied, we have to take into account temperature derating, and so on. And that was fairly easy to find. We got that from the manufacturer website, datasheets, and so on. The equivalent series resistance is actually fairly easy to find. If we idealize this, effectively it's the value of the impedance at the minimum, which is the self-resonance. At self-resonance, the capacitance and inductance, their reactances cancel out, and we are left assuming a very large leakage resistance with just the ESR. So for example, at this curve on the top right-hand side, we can see the ESR is about 20 milliohms for this particular capacitor. The inductance is slightly more involved. Remember, the inductive part dominates after the self-resonance, so we can look at the slope of that inductance trace, and remember that the inductive reactance is 2 pi f times L, so we can pick a point on there and then find an approximate value for L. Or at self-resonance, we know our formula is F equals 1 over 2 pi square root LC, and find in that way. Again, these are all approximations, but good to give you a starting point for your simulation. If you like to simulate the impedance profile of your chosen capacitor, if you figured out certain values using the formulas we just saw, for example, I picked a 10 microfarad Samsung capacitor, and I extracted the values that we have a nominal capacitance, assuming no DC bias, of 10 microfarads. From the self-resonant trough, I saw it was a 5 milliohm equivalent series resistance, and from the high frequency slope, I saw it as about a 350 picohenries of equivalent series inductance. Then I attach an AC voltage source. If I right click on this, all I've done is set an AC amplitude of 1, and I've created a simulation command, which is an AC sweep starting from 100 Hz to 10 MHz. Now if I run this simulation, right click on this plot window and click add trace, we want to plot the impedance profile. So that's the ratio of V1 divided by the current into our circuit. So that's V node 1 divided by IV1, click OK, and here we can see this impedance profile as we saw before. Up to about 2 or 3 megahertz, we have a downward slope where our capacitance dominates. Then we have our self-resonant frequency, which is 1 over 2 pi square root LC, which is C1 and L1 in this case. And above that, we have then the inductance dominates. This 350 picohenry series inductance, which is parasitic and unavoidable, dominates. So this particular capacitor, we can simulate and see how we can get these impedance profile curves ourselves very easily. Again, keep in mind there is far more detail we could go into with capacitors, with derating, frequency responses, non-idealities and so on, but I'd like to keep it brief for this video just to give you a starting point for you to delve deeper. I'll leave some further resources in the links and description section below. The reason why parasitic inductance is incredibly important and why we actually should be aiming to minimize that typically, especially in high-speed digital power distribution networks when we're using these capacitors as decoupling or bypassing, is of course that we saw that the high frequency performance of these capacitors is basically non-existent. The inductance, or this ESL, this intrinsic inductance, is dependent to a large extent on the package size, as we can see here. I took this from a Rick Hartley seminar. For a typical AVX X5R capacitor, just a basic example, we can see that decreasing the package size typically decreases the inductance seen at the terminals. So for example, for 042 SMD, we get about 650 picohenries, and going up to a 1206 part, we get 1250 picohenries. That's why in high-speed digital designs, it's more important that you choose physically smaller capacitors rather than the actual value of capacitance itself. Keep in mind, this is assuming also you've attached your capacitors properly, and properly in this sense is rather vague, to your power distribution network. And you can see this on the bottom-hand side. Not only is the capacitance package size important, but also the mounting mechanism. So how do we place, for example, power and ground vias? Do we route our power? Do we route our ground? And that, of course, will impact the inductance overall, not just the ESL, but the total inductance of our connection very much. For example, the inductance of the connection on the right-hand side with these closely spaced power and ground vias and parallel vias will have a lower inductance connection than the image on the bottom left-hand side with widely spaced singular power and ground vias. Now, of course, this is separate to the ESL of the capacitor. This is just a hint. Not just your ESL of the capacitor is important, specifically for filtering, power delivery, but also your mounting mechanism. All of this being said, in this rather brief video, here are some multi-layer ceramic capacitor part selection guidelines as a very basic starting point, but remember to use simulation and to use your manufacturer tools such as SimSurfing by Murata to help you out. Typically, for power distribution network applications, 20% tolerance is usually fine. You can go with 10% or better if there's no considerable cost difference. For DC rating, I'd suggest choosing at least double the maximum applied voltage. So if you're choosing a capacitor for a USB 2.0 power line, which is normally at 5 volts, I would choose at least a 10 volt DC rated capacitor. But again, check the manufacturer's documentation to be certain, because even with a 10 volt rated capacitor, your capacitance could drop by 80% when you arrive at 5 volts. Choose your dielectric based on the expected worst case temperature range, but also on your application. For both DC and temperature derating, increase the capacitance value to take account for derating and tolerance. This is not, of course, just for DC and temperature, but also for AC and for age and so on. Remember, most things are trying to act to decrease or alter your nominal capacitance. As we saw just now, the package size is important, so the higher the frequency you'd like to, for example, decouple or filter, the smaller the capacitor package should be, and typically that will also inhibit the maximum capacitance value you can get. Smaller packages typically have smaller maximum capacitances, smaller maximum DC ratings, but typically better high frequency performance due to lower ESR, lower ESL. So this, again, is a trade-off. I'd strongly suggest checking out your manufacturer's part search, your distributor's part search to see this in action. Again, as we saw before, if we want to design audio circuitry, try to avoid class 2 ceramics in the signal path due to piezoelectric effects, microphonics, and so on. I'd suggest using NPO or COG type instead, which are class 1 multi-layer ceramic capacitors. The problem is with those capacitors, they're more expensive typically, and they're only available as small value caps, so typically up to about 10 nanofarads or less. Let's look at some very basic and brief examples. For example, for this FPGA-based hardware design, I have some decoupling capacitors on the bottom side of this BGA package. You can see these are 0201 parts because they had to fit between these through-hole vias on the bottom side. So that was already one limitation, which made me go to 0201 for some of these capacitances. Keep in mind that 0201, because of their smaller package size, will have a lower inductance, of course, assuming they're mounted correctly. In the actual schematic, these are, for example, these 100 nanofarad caps here. I use some on these 1.0 volt rails, some on these 3.3 volt rails, and these are the same part due to bill of material consolidation. And these are the capacitors I actually ended up choosing. These are X5R. I didn't have particular strict temperature ranges, so X5R being fairly inexpensive was okay. 100 nanofarads nominal, 20%. It doesn't really matter for this application, having such a large variation. They are power decoupling capacitors. Size, of course, important, and of course the voltage rating. We saw 3.3 volts is the maximum applied DC bias, so at least double that. So I could have gone with a 6.3 volt rated capacitor. 10 volts is giving me an additional safety margin. Plus, they're available in very large quantities and they're very, very cheap as well. Again, going to the sim surfing tool for this particular part, we can see at 0 volts bias, of course, it's 100 nanofarads. But if we go to 3.3 volts, we've dropped to about 60 nanofarads, which is still completely fine, but it's still a 40% drop, which is quite significant. So if I'd gone with a 6.3 volt maximum rated part, I might have dropped 60 or 80%. So that's why I went with a 10 volt part. On the same board, I also have some audio circuitry with some op-amps doing some filtering, and these particular capacitors are either tantalum type, so they're not class 2 ceramic capacitors, or they're class 1 COG capacitors. COG, for example, this one here is 1.5 nanofarad capacitor. This one here, we can see this is a class 1 type, so it's COG or NPO. I chose a larger package. It's a 50 volt rating, so they typically will have higher ratings as well, much better tolerances, and again, they won't have this microphonic behavior, which you don't want in the signal path. But they are more expensive typically, and they only exist in fairly small capacitance values. But that's why I would go with a COG type, a class 1 type here. That's why you see these fairly small capacitance values here, because they're all not class 2 multi-layer ceramic capacitors. For decoupling of the op-amps, I go with a 100 nanofarad class 2 ceramic capacitor, this time an 0402 rated to 50 volts. This is a very standard generic part. Also a different project looking at the microcontroller for the load capacitors of this crystal. These 10 picofarad capacitors are also type COG because any variation in this capacitance will throw off the center frequency of this oscillator circuit. So you want them fairly good tolerance, no drift with temperature or with applied DC voltage. And that's why for a crystal oscillator section, you would typically go with COG class 1 type multilayer ceramic capacitors. Thank you very much for watching this video. I hope it was useful and I hope it exposed you to some of the main ideas when it comes to choosing and selecting SMD ceramic capacitors. I've made this video because in the future I'll be making some videos on filtering, and this is kind of a prerequisite to those videos. To make sure you don't miss out on any future hardware design, DSP, embedded systems videos, make sure to subscribe, like the video if you like the video, leave a comment if you have any questions, and I look forward to seeing you in the next one. Bye bye.